So if the size of the effect is greater, that's going to increase your chances of getting a significant p-value. That's therefore going to increase your statistical power. If the variability of the thing you're looking at is higher, if there's more variability is going to make it harder to find an effect, harder to get a significant p-value, so that's going to decrease your statistical power. Bigger sample sizes, of course, are going to increase your statistical power. Finally, of course, we can play with the significance level. A typical study might set the significance level at 0.05, but that's not the only way you can do it. Sometimes the significance level might be set at something lower, like 0.01. Well, 0.01 is going to mean your type 1 error rate is lower than 0.05, and there's a direct trade-off between type 1 and type 2 error. If you require a more stringent p-value cutoff, like 0.01 rather than 0.05, if you want a more stronger significance level, a smaller significance level, then that's going to actually decrease your statistical power. It's harder to find a p-value of 0.01 than it is to find a p-value of 0.05, so that's going to decrease your statistical power. Notice that all of those four elements, we could put them together. We could put those together and make a formula that tells us how big we need to design our studies in order to have sufficient statistical power. If you look at all the things that affect power, the one that's really most under control, the control of the investigator, is the sample size. The investigator can't really change the size of the effect or the standard deviation, the variability. The investigator can change the significance level, but there may be particular reasons that we have to set it at 0.01 or 0.05. So what's really under the control of the investigator in terms of influencing the statistical power of a given study is the sample size. So when we plan studies, we actually sit down before the study starts and determine how big of a sample size do I need in order to have a sufficiently powered study. Those sample size formulas are directly related to putting those elements together. So power and sample size are directly related to one another, and those are affected by the effect size, the standard deviation, and the significance level. We can put all those 5 elements together into formulas that tell us how big of an N, how big of a sample do I need for a given level of power for my study. I'm just going to put one formula up, one sample size formula up on the screen here so we can talk about it. I'm not expecting you to want to memorize or even use this formula at this point. If you want to know more about sample size formulas, like the sample size calculation, there's an entire optional module you can take to learn about all the details of this formula. But what I really want everybody to get out of here is just the relationships between those 5 elements that I just talked about. Those 5 elements relate, and you can put them together to come up with a sample size formula. So for example, this formula says that the sample size that you need in each group is directly related to variability, the power you want, the significance level you want, and the effect size you want. The variability is in the numerator. So if the outcome is more highly variable, then for a given power, you're going to need a greater sample size to achieve that power. The N is going to be bigger because variability is in the numerator. Z beta is how we abbreviate power. If you want a bigger power, if you want power more than 80%, you're going to need a bigger N. So again, power is in the numerator. You're going to need a bigger N if you want more power. If you change your significance level to be more stringent, say again 0.05 down to 0.01, if you want a higher level of statistical significance, then that's in the numerator too, so you're again going to need a bigger sample size. However, if the effect size is bigger, the effect size in the real world, the true effect is bigger, that's in the denominator. So to find a bigger effect size, you actually need a smaller sample size. If the effect size is big, it's going to take less people in your study to find it. So we can plug in some numbers, some assumptions into a formula like this and come out with the approximate sample size that we need in our study to have sufficient power. Again, if you want more details about the exact derivation of this sample size formula and formulas like it, you can refer to the optional module on sample size calculations.